I'll try and merge them together on my slides. So the first presentation is mostly on, I'm going to build on what Mr. Sinha said, Mr. Storm said, and Mr. Mohanty said. So I'll build on that, and then I'll move on to incentives for coal units. So I'm going to skip on my company details. But I think some of the things that you've already heard is, there are some flexibility themes. What do you really need from a power plant, right? So you can have startup times, you can have turndowns, you can have emissions compliance, still a new phenomenon in India, but I can guarantee you, just like renewables have come, I know there's already some regulation on emissions. So you might have extremely strict emissions compliance requirements in the future. And then there's ramp rates, and ramp rates could be both from a startup standpoint or from a low load standpoint. So you sort of have to identify what's important for your physical asset. In terms of the impact, safety is number one. And I'll show you some examples where there have been a few near misses where people have just about saved themselves. They could have died with flexible operation. I mean, it's possible when you run baseload units that you could have a safety issue, but with cycling operation, this is something new, so something to keep in mind. Obviously, equipment life is an issue, reliability, costs, and revenue. So all of those things. And then something that Mr. Sinha and Stephen mentioned is, how do you mitigate all of these? So there's operational adjustments, there's capital improvements, and then, you have to sort of assess what's most valuable to you. So this is still the problem statement. And so you need incentives for your existing power plants to actually perform flexible operation. Mr. Mohanty from GE said, you can do all these things, but then, you need some incentive to actually invest in a unit like that. Now, you can see that unhappy power plant. It's not unhappy because you're cycling the unit. It's totally okay if you actually operate units in flexible mode. I mean, you've heard from the German case, or if you go to the South African case or the US case where Stephen said that, Duke Energy has seen a dramatic drop in capacity factors. It's just a fact of life. The coal plants will have to operate in a flexible mode. The only thing that's missing there is how do you compensate that coal plant? You've got stranded assets. I mean, you're not going to shut down all your coal plants because you have renewables. You still need operating reserves. The previous session had all of these different percentages of operating reserves that you need. So you still need the coal plant. So as far as you can actually give it the compensation for providing the flexibility, you're in good shape. So that plant can be happy again. So what? I mean, Stephen's already mentioned this. I'm not going to spend a lot of time, but between the panel here, we could actually write about a 200-page document just right now listing all the problems that you can get on a coal plant or a gas plant. In fact, if you cycle a wind power plant, which they cycle anyways, you see damage even on a wind farm. So it doesn't matter. Cycling in general is not what units are designed for. So you will see a long list, and I will not go through it. So here's our viewpoint. Again, any unit can be cycled, and with minimal capital investment. In fact, like Mr. Sinha said, you can actually take an existing baseload design coal plant and cycle it pretty much every week, and you might see actually no problems for the next 2 or 3 years. You will eventually have some problems, but it doesn't mean that you can't cycle a unit. You just have to keep in mind that by cycling the unit, you will actually do damage. It's similar to your own body. If you're actually, running on the road all the time, you're going to hurt your knees at some point. So it's the same thing on a power plant. You're going to have some wear and tear damage, and there's a penalty. So you need to be able to recover that cost. So in India's case, you can recover the higher heat rate penalty that you do when you run at low load, but you can't do it in every state, as I understand. So that is okay, but then you also have the additional cost of O&M, training, and equipment efficiency that you need to take into account. So strategy similar to what Stephen mentioned. Again, you have to define the metrics. You need to do some analysis. You need to do testing. You need to do training. You need to revise the operating procedures based on that. And then you need to do an economic evaluation. So I'm going to show you some things that, and again, it's an EPRI document. So we all work together here. You can take a look at that EPRI product ID. If you're members, you can get that information. But these are some of the steps. So there's steps that you can take before an outage occurs. So what can you do? You can do peer review, you can do economic analysis, you can come up with metrics such as equivalent hot starts and operating hours. You can do troubleshooting, audits of design. You can identify what attributes are actually associated with damage mechanisms. You can collect that information. You can evaluate a lot of the operating data. I know NTPC does a lot of M&D data. They collect all this information. So these are all the things that you need to do before you actually get into flexible operation. Now, there's two things that can happen during maintenance. You can actually plan for an outage, or you can have an unplanned outage. In either situation, you need to sort of, hopefully in the planned setup, you actually change your inspection locations. You're actually looking at if you are operating in flexible operation, where should I do ND, what kind of maintenance I need to do, and obviously on an unplanned situation, you got to fix everything. Now, in terms of mitigation, you have three of these options, right? You can continuously repair and maintain, or you can do operational or control changes, or you can do design changes. So again, three options in a mitigation stage. And so in terms of defining metrics, I mentioned equivalent hot starts. Here's an example of defining metrics. So, you can have low load operation, you can have, some amount of damage from that. If you do cold starts, you get an extra more damage, so you come up with some of these metrics. And then you have to keep in mind some of the things that can happen. So you have to look at cycle chemistry, cyclic stresses, fatigue damage, the type of cycles you do, the thermal gradient on the components, the materials. So all of those things have to be kept in mind when you're doing you're defining the metrics. And here's a whole list of factors affecting power plants. I'm not going to go through all of them, but one of the things you need to keep in mind is, what type of operation has this plant done historically and the type of maintenance that you've done on the unit. Here's some examples of transient analysis. We're using rainflow cycle counting, and we're actually looking at different components, and we're looking at, all I'm showing you there is you can define different exponents. I'm not going to get into stresses here, but you can actually measure how much damage you get from different types of transients. So on the left-hand side, I'm showing you economizer cycles. On the right-hand side, I'm showing you superheater cycles. So this is a case where we took a 700 megawatt unit, subcritical 700 megawatt unit, and made it go through 2 shift cycles, so as a test program, and then calculated how much damage was happening at each location on the plant, so that you can compare different starts, different operating modes to try and estimate how much extra damage you get from different components. I'll skip this slide in the interest of time. Here's some more, when you're defining the metrics, you want to sort of identify locations in the power plant that you're likely to have, say, for example, corrosion fatigue damage. So here's some examples of that. Now, this thing is very similar to what Stephen showed. Here's an example of positive and negative control parameters that you have when you, say, for example, do shutdown operation. So on the left-hand side, I have all the negative effects, and on the right-hand side, I have the control effects that can give you some positive effects. It's difficult for you to read all of this, but we are looking at, so if you're doing shutdown, I'll go very quickly, some of the options that you have. You have forced cooling, you have natural cooling, you have controlled shutdown, you have pumps, vents, you can bottle up the furnace, so you have all these options. And within those options, you can have all of these different negative effects and positive control factors. So this is just a roadmap, the type of analysis that Stephen's recommending and that we are recommending is what you need to do. It's not rocket science, it's just some of the step-by-step process that you need to take. And then I have a similar chart for low load operation. So there's positives and negatives of doing that as well. And then you need to get specific. So here's an example of actually looking at economizer inlet header cracking. There's a flow chart there. How do you go about looking into all of these options? So not going to spend much time on this. Let me move over to my other slide deck, and I'll finish that pretty quickly. Can you put that up? Okay, we'll do that. Okay. All right, so let's talk about incentives for coal plants. Why should they actually go and do all of this? So here's very briefly our goal, right? I mean, we need grid flexibility, so for that we need incentives. And the goal is more RE on the grid. So you need generator flexibility to actually allow for more RE. Here's what happens to the conventional fleet. Maintenance and overhaul costs go up, forced outage rates go up, emissions per megawatt hour generated go up, long-term production costs in the unit might go up. So when you're in a dispatch center, we're talking about production costs. In the immediate moment, production costs will go down, but in the long run, production cost is going to go up. Revenue goes down, efficiency goes down, capacity factors go down, and life expectancy goes down. So in terms of the things that you can do for grid flexibility, you have system operations, market mechanism, conventional generation, demand-side management, grid networks, and storage. I'm only going to focus on the second and third block over here. So again, grid flexibility, here's your options, right? And I'll spend a couple of minutes on this. So you got frequency response, you got frequency regulation, you got spinning reserve, non-spin reserve, and ramping. So, and what I have on the second level there is, the time scale that we have to do this, right? So frequency response is immediate response, and ramping, if you listen to the Cal ISO case, is a 5-minute response. In between that, on the non-spin, you could be 10 to 30 minutes, and spinning reserve is 10 minutes. So frequency response, there's no market for that. Frequency regulation, at least in the US, we have an auction system. So you actually have, you put your requirements, and then somebody actually says, okay, yes, I can provide that, so there's an auction. Similarly, spinning reserve, you have the same thing, non-spinning reserve, the same thing, in the market scenario in the US. In terms of ramping, California ISO has a mechanism where they'll actually compensate you for providing ramping capabilities. So when we talk about power plant flexibility, these are the three categories that we're looking at, right? We're looking at the range of flexibility that you can do. You're looking at the ramp rates, but you're also looking at for how long you can do that type of operation. So if you can go down to 30% min load, but you can only do that for 1 hour, it's probably not worth that much effort. So you need to sort of define how long you need that low load operation for. Here are the wholesale prices in the US. So what you can see is in 2007 or 8, you were getting on the median $60 per megawatt hour. It costs about $30, $31, $32 per megawatt hour for a coal plant to actually break even. So at $60 a megawatt hour, it could make a lot of money, mostly driven by natural gas prices. But take a look at what happened right from 2008 till about 2017. For several years, the price that you could get in the market was lower than your break-even cost of generating electricity from a coal plant. That's part of the reason why just 5 years ago, the US used to get more than 50% of its power from coal. Today it's down to 30% and might fall to about 27% next year. So that's how dramatically that's happened. Now, if I showed you another chart, you could see about 6,000% increase in wind generation in the US along that same curve. Now, most people think that it was the wind and the solar that might have caused a drop in the wholesale prices. That's actually not true. 60 or 70% of the drop in prices come from the fact that natural gas price has gone down in the US. Only about 4 or 5% of that drop in pricing is attributable to renewables. So now that's not to say that renewables had no effect. So as you add more and more renewables, because you can go to the German case or you can go to some other countries where you will see that big impact that renewables will cause depressed wholesale prices. So you can't recover that cost. So I just wanted to show you that just recently we can see coal plants still going to be able to make some money, but for about the last 3 years they were not in the money. I've already talked about this. So I am going to show you some examples. Actually, never mind. But you have the references here, so I won't talk about that. Here are some cost parameters. We've given you the link for taking a look at some of the scatter of cycling costs that we've observed around the world for power plants. So what I have there is on the x-axis, I have the size of the unit. On the y-axis, I have the cost per megawatt capacity for cycling costs. And so here's where I want to talk about. So, okay, here are some of the incentives that are available today. Short-term pricing intervals, right? So one of the things that FERC in the US has done is require that, we keep talking about settlements in 5 minutes, right? What they're saying is that they're settling what dispatch you get in 5 minutes. But what was happening was that the compensation settlement or the price settlement was happening at 1 hour level. So there's some disconnect between how you were dispatched and how you were getting paid for it. So now with the FERC order, you will actually do pricing and the dispatch settlement at a 5-minute interval. So this gives you, the plant operator, an incentive to actually perform to changing requirements from the grid. So that's a good thing. Pay for performance is another thing that's come up. So FERC Order 755 originally came for batteries, but it applies to all power plants. So you don't get paid if you don't perform. In the past, what would happen is that if you had a 5-minute change in market price, there was no incentive for the coal plant to go any faster or slower. It could go take its easy time because you're getting compensated at the higher market price. So now there's a pay for performance requirement on the grid code for you to be able to do that. Flexible ramping, I already mentioned, California ISO does that. Here's another thing, real-time price adder. So that is actually, it happens in Texas, in ERCOT, where based on the scarcity of flexibility on the grid, you can actually get paid extra. So they set an upper limit to how much you can get paid. In Texas, right now, that value is $9,000 per megawatt hour, right? That's the upper limit. 2 weeks ago, when I was making this presentation, on that day, I have that chart from Bloomberg, it actually happened in Texas. We actually had a situation where the wind died, there was a significant reduction in flexible capacity on the grid, and it gets triggered by the operating reserves in the market. And actually, for 3 hours, the rate in the market was $9,000 per megawatt hour. So the entire state of Texas, mostly, all the power plants were able to get that much money. So you can make a lot of money from that. There's another one where resource adequacy. This is another one that Cal ISO mentioned, is procurement of fast response capacity. So if you're a coal plant, say you put GE's flexible operation, retrofit, then there's actually an incentive for you to actually participate in that market. And one last thing that I'll say is capacity markets, right? That's not the solution for everything. ERCOT, for example, is an energy-only market, and in fact, the cost of operating reserves in ERCOT is about 7% lower than, say, Cal ISO or New York ISO. So capacity markets are not something that will solve everything. You can have an energy-only market and still you can still incentivize people. So final slide here. Here are some things that have actually happened. So this is a possible solution for the Indian case. In Alberta and Canada, what they did was they had PPAs for all the units, and they actually had a cycling and flexibility component in the power purchase agreement from the beginning. So if you, the buyer of that electricity, were forcing the generator to cycle, you had to pay them for performing that flexibility. So they actually had limits on how many cycles that unit could do, and then there was penalties for doing more or less. So that's that. Unintended consequences, since we talked about energy storage. Here's one example. Actually, batteries, when you cycle, don't have that much life. I won't spend too much. I actually won't talk about this, but there's a big 100 megawatt battery that actually has cut its life into half because of cycling operation that the markets made it do. So you can read a little bit more about it. So I'll stop here.